What if I told you there was a whole era of our universe's history that we can't see? No stars, no galaxies, just endless darkness. Welcome to the cosmic dark ages. After the Big Bang and before the first stars turned on, our universe was in a weird state. There was stuff in it, but we couldn't see anything. It was completely dark, and it lasted for hundreds of millions of years, but why don't we know more about it? And what could new telescopes like JWST teach us about this mysterious period? To answer these questions, let's start at the beginning. Well, not the beginning, like the actual beginning with the Big Bang, but a beginning for this story. This is our universe about 380,000 years after the Big Bang. At this point, the universe has expanded and cooled enough for the simplest atoms, hydrogen and helium, to form. Before this, the universe was a hot, dense plasma where nuclei couldn't form because the extreme heat kept ripping them apart. So, if the universe was already mostly hydrogen and helium, why was it so dark? Where were all the stars? Well, the reason is pretty simple. Stars need some way to get started. You need some way to build up a big ball of gas that's massive enough to collapse under its own gravity. The issue is that in the early universe, everything was flying away from each other so fast due to the expansion of the universe that nothing had a chance to clump together. The only thing that would have been able to overcome the expansion and pull things together was a huge concentration of mass. But such objects were extremely unlikely to have formed in the early universe. There simply wasn't enough matter around. Okay, fair enough, but surely over hundreds of millions of years, things would have had a chance to clump together, right? Yes, they would have, but there was another problem. It was still too hot. For example, the only way that protons and neutrons could have combined to make nuclei of heavier elements was for something to get really, really close. They needed to be close enough to overcome the electromagnetic repulsion between the protons, which means they needed to be close enough to experience the strong nuclear force. The trouble is that if you get close enough to something to experience the strong nuclear force, you're also close enough to experience the other force, the strong force, which will blow you apart. So if you want to make a heavy nucleus, you need temperatures and densities high enough to overcome the electrostatic repulsion, but not so high that they rip your nucleons apart. That delicate balance required for nuclear fusion only happens inside of stars. And since there weren't any stars at this point, that meant that atomic nuclei heavier than helium couldn't form. And since those heavier nuclei are what makes light elements like oxygen and carbon, there was essentially no matter around except for hydrogen and helium. This may sound like a disappointment, but for astronomers studying the early universe, this is actually great news. The fact that only hydrogen and helium were around at this time means that the universe was very simple, making it much easier to model and study. And it turns out that the conditions in the early universe never did allow for the formation of those heavier nuclei. Even though the universe expanded and cooled, it didn't cool enough. So the only abundant elements in the early universe were hydrogen and helium. And without heavier elements, star formation was impossible. So the universe remained dark, and that raises an obvious question: how long did this last? Well, unfortunately, it's hard to say exactly. We know it ended when the first stars formed, but we don't know when that happened. Current estimates suggest that it happened somewhere between 150 million and 200 million years after the Big Bang, but it could have been sooner or later. The end of the cosmic dark ages might have been quite a violent period, too. As stars ignited and exploded, the universe would have been filled with powerful blasts of radiation and matter. This is known as cosmic ionization. As the first stars blew up, they released a tremendous amount of ultraviolet radiation, which ripped hydrogen atoms apart and created a sea of free electrons and protons. But unlike today, there were no heavier elements around to capture those electrons and form neutral hydrogen. So the universe became filled with a fog of ionized gas. These free electrons would have scattered light, preventing photons from traveling very far. This is different from the neutral hydrogen that makes up the cosmic microwave background, or CMB for short. The photons in the CMB were able to travel freely across the universe. Once the universe cooled enough to form neutral hydrogen, this meant that light could once again travel freely through space. We call this epoch the Cosmic Dark Ages because although there was stuff in the universe, we can't see anything. The universe was dark. No light was able to travel far enough to reach us. The only light we can see today is that which has been stretched by the expansion of the universe from when the universe was much smaller. And since the universe was so hot when it was small, most of that light was in the form of the CMB. But that's not the only reason. The universe was dark. You see, while the CMB represents the light that was around 380,000 years after the Big Bang, the universe was still too hot for nuclear fusion to occur and stars to form. It would take another 100 million or so years for the universe to cool enough for the first stars to ignite. And since the universe was still mostly hydrogen and helium, which can't form stars on their own, this meant that the universe remained dark until the first stars turned on. So this leaves us with a few questions. How do we know anything about this era? What does it tell us about the universe? And what might new telescopes teach us about it? First off, as I said, the universe was dark, so we can't directly observe the cosmic dark ages. However, we can indirectly study it. For example, one way we learn about the early universe is by looking at the cosmic microwave background, or CMB for short. You see, the CMB is the light that was around 380,000 years after the Big Bang, but since the universe was still hot and filled with free electrons, it was opaque. Photons could only travel very short distances before getting absorbed by one of those electrons. This meant that the light we see today was emitted when the universe was much smaller. By studying tiny variations in temperature and polarization in the CMB, we can learn about the early universe. These variations represent tiny overdensities of matter in the early universe. Because the CMB was emitted from a much smaller universe, these overdensities correspond to places where there was slightly more matter. And over time, those denser regions grew into the galaxies we see today. Another way scientists have learned about the early universe is by studying quasars. Quasars are supermassive black holes at the center of galaxies. They grow by consuming the surrounding gas and dust, and as they consume this matter, they emit tremendous amounts of light. In fact, quasars are among the brightest objects in the universe. Some of the light they emit is in the form of powerful jets of radiation. These jets can extend thousands of light years away from the black hole. And while they're shooting away from Earth, they're actually moving in the opposite direction. This means that if we look far enough into space, we should be able to find the remnants of ancient jets that have been stretched by the expansion of the universe. Such relics can tell us about the early stages of galaxy formation because they depend on both the mass of the black hole and the distribution of matter in the early universe. Now, what can we learn from this dark era? One thing it tells us is that the universe was very simple. There were only two elements around, hydrogen and helium, and there were no stars. This makes the early universe very easy to model, which is great news for astronomers. It means that we can use computer simulations to try to recreate the early universe and see how it evolved into the universe we see today. It also tells us that the universe was expanding. If the universe wasn't expanding, then maybe matter would have had a chance to clump together and form stars. But the fact that everything was flying apart meant that star formation was impossible. And finally, it tells us that the universe was cooling. If the universe wasn't cooling, then maybe those heavy nuclei would have had a chance to form. But since the universe was cooling, the only elements that could form were hydrogen and helium. So what's next? What will we learn about the cosmic dark ages in the future? Well, we'll continue to study the CMB, but we'll need new and better telescopes to do it. For example, there's the Atacama hole in northern Chile, which aims to measure tiny variations in the polarization of the CMB. These variations will help us map out the large-scale structure of the early universe. There's also the Square Kilometer Array, which will survey the entire sky every 6 days. This will allow us to search for relics from the early universe. Then there's JWST, which won't directly observe the cosmic dark ages, but will look at what came after. JWST will be able to see the light from the first stars and galaxies, which will help us understand how the universe went from being dark to illuminated. All of these telescopes will help us understand one of the most mysterious periods in the history of the universe. The cosmic dark ages. After the Big Bang, the universe went through a period of darkness that lasted for hundreds of millions of years. It was dark because there were no stars, and it was also dark because even if there were stars, the universe was too hot for light to travel far. But eventually, the universe cooled enough for the first stars to form and light flooded the universe. All of these telescopes will help us understand one of the most mysterious periods in the history of the universe. I hope you enjoyed this video. If you did, don't forget to subscribe so you don't miss the next video. Thanks for watching.